All right, so we're on to 1.8 part 2, looking at different ways to combine functions. Part 1, we talked about adding, subtracting, multiplying, dividing, doing those operations between two functions. Today we're going to talk about composition of functions when you compose them. Basically, it means you do one function and then you take that and you plug it into another function. So it's like a two-part or a three-part process depending on how many compositions you want to do. It's like you take the answer for something and it becomes the input for the next one. So we do this all the time in real life situations. We'll look at one at the end of class today, looking at how you calculate a sale price and then the price with tax. You need to do one operation first, and then you compose it or you put it together with another operation to get to your final result. So we're going to use composition of one function with another function and use that in a real life setting. So that's kind of our essential question for today. All right, so let's take a look at what composition of function is defined to be. So when you see composition, so it's the name of a new operation. The symbol for composition is an open circle. So you'll see this open circle. So this first part, F composed with G is how you would say that, or f of g of x. That's the name of the function. So that just like when we had a plus sign yesterday or a minus sign in between there, this is telling you, this first set of parentheses, that hey, you're going to use the function f and the function g and you are going to compose them. So kind of the shortcut is compose. Just like if you have addition, you would call it add. Composition, we call composing or compose. Kind of like making music, right? Our mathematical music here. So we're going to compose two functions. And then x, again, is just the variable that we're using to write the rule. So once again, this is not multiplication. Just because you see two sets of parentheses, it means, hey, this is the name of the function and this is the variable we're using to describe it. And this is what it means. Composition means f of g of x. So it's f of g of x. So it means that you take the function g and you substitute it into the function f for that variable x. You're actually putting an entire rule into the function. So instead of like f of 7, you're doing f of the entire rule for g of x, whatever that is. So let's talk domain for a second when you do that. So when you compose two functions, you got to be careful about, again, the numbers that you're using. The domain of this composition of f composed with g, so f composed with g, that's how you'd say that. It's the set of all x's that are in the domain of g, so they have to work in g, so that when you do g of x, when you actually do g of that value, that output, whatever the output is for that, is in the domain of f. So think of it like you're going to take this function g and you're going to do g of x. And whatever those numbers are, you're going to put it into the function f. And this output, whatever that answer is, when you plug it in, so that output you get when you do g of x and you get this answer, whatever it is, and you plug it into f, it has to make that function a real number answer. So when you're thinking about it, it's got to work in g, and then once you substitute that number into g, the output of g of x, whatever that output is, has got to work in the domain of f. So it's got to work in both. Let's talk about how you actually do the composition then. You just substitute the one function into the function f for the x. So just like you would do an f of 7, you'd plug the 7 in for all the x's. When you do f composed with g, and remember that means f of g of x, that means you're going to substitute the function g of x into the equation f everywhere you have an x. So it's a substitution. You're substituting. So we're going to be putting in expressions, and that's how we find those values. So f composed with g. Now you can compose functions in either order. You could also do g composed with f. The one way I can kind of help remember this is like, which one am I supposed to substitute? Like you may remember, oh, it's something about substitution. What does that mean? It's always the second function that gets substituted. So the second function is the one that you substitute. So second and substitute, they both start with S. I don't know. Substitute. If that helps you remember, that might be a little bit easier to think of it that way. All right, so let's practice one. We're going to do just some practicing, and then we'll look at a real life example. We'll also talk about domain. If you're working with things that have domains of all reals, I don't really have to worry about the composition domain because what I'm making also will have this domain of reals. But if I have things that have limitations, I do have to be careful with domain. All right, so here are my two functions that we're going to work with in example 2, f of x and g of x. f of x is a linear equation, so this is a line, degree 1, and then degree 2, that means we're going to have a parabola or a quadratic for degree 2. So for g of x, we're composing it with a quadratic. So first thing we're going to do is we're going to find f composed with g of x. So we're going to do that first, and then we're going to do g composed with f. Then we're just going to compare the results and see what happens. So f composed with g of x. Notice how I said that. F composed with g. That open circle means composition. That means f of g of x. So I'm going to be doing some color coding here so we can talk about that. So that means we're going to be taking g of x, the rule for g of x. So I'm going to go ahead and highlight this. So the rule for g of x is going to get substituted into the function f for the x. So it's just like saying f of 2x squared minus 1, because g of x is the 2x squared minus 1. So I'm going to replace this x with the function g, that entire rule. So that means, okay, what does the rule for f say? It says 3 times what you substitute plus 4. So that means 3 times what I'm substituting, which is all of g of x, and then plus 4. Now, if it's easier for you to imagine, like, hey, what would I do for f of 7 and think of it that way? It's the same process. You'd be doing 3 times 7 plus 4, right? Well, this is no different. It's just instead of substituting a 7, gosh, you're substituting an entire rule, right? That all of g of x. So it's really the same process. It's a substitution. Now, from here to the end, it's just making this easier to deal with. So distributing, putting together like terms to figure out what f composed with g of x really is going to be. So f composed with g, we're making a new function here, will be this simplified. So we've got, looks like what, 6x squared minus 3 and then a plus 4. So we've got 6x squared plus 1. Notice what I made here. F composed with g, I made a new parabola. You're making a new function. All right, so what does it mean then to do g composed with f in the other order? So g composed with f. So make sure you're using the language correctly there. G composed with f. Well, that means g of f of x. That means the second function is now the f of x, not the g of x. I'm going to be substituting the other way. I'm going to be plugging in the function f into g. Remember, whichever function comes second, that's what gets substituted. So let's see what that looks like. I'm going to go ahead and kind of get rid of my highlighting here so we can go the other direction. That means I'm going to be taking the entire function f, so the 3x plus 4, and I'm going to be replacing it into the function g for any x's that I see over there. And I only see the 1, it's being squared, multiplied by 2. But this 3x plus 4 is going to go in place of the x in the function g. So I'm going to be putting 3x plus 4 into the rule for g, just like normal substitution. So I'm going to be putting 3x plus 4 in. So the rule for g says, okay, do 2 times what you're substituting, which is my 3x plus 4, square it and subtract the 1. Now we got to be careful with order of operations, but that's what the rule says. So when we plug that in there, so this is going to be g of f. Now before we do the calculating of that, the order of operations, I just want you to guess. Do you think f composed with g is going to have the same answer as g composed with f? Do you think if you compose them in the opposite order that you should get the same answer? And then let's just double check. So let's talk order of operations. So let's take a look here. I have multiplying by 2, I have squaring, and I have subtracting. Let's think PEMDAS here. Please excuse my dear Aunt Sally. Parentheses, exponents, multiply, divide, add, subtract. Okay, so parentheses, there's nothing really to do in there because they're not like terms, but I need to do exponents next. So just be careful. The first thing that you should do should be square that 3x plus 4, which does not mean just the 3x squared and the 4 squared. It means first, outside, inside, last. It means distributive property, or FOIL if you'd prefer. So I'm going to have you go ahead and do that distributing, and then do the multiply by 2 and the subtract 1 and see what you end up with. So go ahead, pause the video and give it a try. Alrighty, so let's take a look at your arithmetic and see how you did. So FOIL, first of all, should have given you this. So we had 9x squared plus 24x plus 16. Then we have to distribute through the 2, and then we have to combine our like terms. So if you notice, we made a new parabola. It's degree 2, but does it match the parabola from f composed with g? No, it's completely different. So what you're going to find is if you compose two functions that are very different, in the opposite order, you're not really going to get the same thing. Now there's a really special case in which you do. So if you do F composed with G and G composed with F and you get the same answer, kind of a unique situation. We're going to talk about what that means in a future lesson here. So we'll watch for that. But for most situations, those are not going to be the same. So let's practice this composition just a little bit more, and then we'll do some application. So we're going to start with two different functions, F composed with G and G composed with F. So here's F of X. So it looks like we have 2x plus 5, degree 1. So what's that? Linear. And then G of X is quadratic at degree 2. So very similar to what we had before. So we're going to do G of F and F of G. Said that backwards when I underlined them, but F of G and G of F. So F composed with G and G composed with F. Again, probably not going to get the same answer. So we're going to do those calculations. And then we're going to actually evaluate at a particular number. So taking those new functions we make and evaluating at a particular answer and see what that looks like. All right, so we're going to go ahead, and this is going to give us a little bit more practice in this and do part A. We're going to do F composed with G first. Remember, that means F of G of X. So that means the second function name, G, is going to get substituted into F. So that means I'm going to be taking the rule for G and I'm going to be replacing it into the function F for that X. That means I'm going to be doing F of 4x squared plus 1. So I'm going to be doing that rule. Okay, so what does that mean? Well, the rule for F says take 2 times what you substitute, so 2 times the 4x squared plus 1, and then plus 5. Don't forget the constant there, so plus 5. So we have F composed with G of X. Let's do our simplifying here. We're going to distribute. So that would be 8x squared plus 2, and then plus 5, so plus 7. So we made a new parabola. So F composed with G. Now let's do G composed with F. And again, go ahead, if you want, pause the video, see if you can successfully figure out what this means and then what it would be, and see if that works out for you. So G of F of X, it means we're going to take that second function F and we're going to plug it into G. So I'm going to erase this so I can do my color coding here. That means the function F, this linear equation, is going to have to be substituted in for the X in the function G. So that means G of 2x plus 5. So I'm replacing everywhere I have an X in the function G with that entire rule for F. So the rule for G says take 4 times what you're substituting, which in my case is 2x plus 5. I got to square that and then add 1. So careful on order of operations here. I have to square that first, which means, remember, 2x plus 5 times 2x plus 5. Then I'm going to distribute by the 4, and then I'm going to add the 1. So go ahead and pause the video, see what you come up with for arithmetic. Alrighty, so let's take a peek at the arithmetic. So first things first, we had to distribute or FOIL the two binomials together. So that should have given you that. Then you're going to distribute through by the 4, which gives you this. And then we add the 1, which gets us down to our G of F of X. G composed with F. So notice, F composed with G from the first part is most definitely not the same parabola as G composed with F. So we get two different rules. So, and often that will be the case. All right, so what I want you to do last. So what does this mean? Take a look at part C. F composed with G of -1/2. Well, what does it mean when we put in a number in place of the X? Well, it means they want us to evaluate that function at the value -1/2. So make sure you use the right one. F composed with G was what we did in part A, right? So our rule for that is the 8x squared plus 7. So make sure we use the right rule. So I'm going to go ahead and use part C here. I'm going to give ourselves some room. We want to do F composed with G of -1/2. So that means I'm going to use the rule for F composed with G of X, that 8x squared plus 7, and I'm going to substitute or evaluate at -1/2. So I'm going to take that function that we had and I'm going to evaluate at -1/2. Well, that just means I'm going to do like what I've always done. I'm going to plug in -1/2 everywhere I see the X, which is just one spot, and I'm going to do the arithmetic. So -1/2 squared, and then times 8, and then plus 7. So negative 1/2 squared, that would be positive 1/4. 1/4 times 8 would be 2. 2 plus 7 looks like 9. So my output would be 9. I can evaluate this function at any number I want. I created a new thing with composition, and I can replace with values as well. So that's something that we definitely want to be able to do. All right, let's take a look at a couple other options here when we think about domain. So when I'm looking at composition, again, I have to be careful about what I create and what I'm going to be able to use. So let's take a look at this. So if they want us to do f composed with g, we're going to use the square root function, and we're going to use the g of x function. So g of x is just linear. That's no problem. The domain is all reals for this function. So I can use anything I want for a line. But we got to be careful in the square root function. I can only use values that are bigger than 0, right? Remember, I can't use anything that that makes my value negative underneath. But when I put them together, I have to take a look. It has to be the ones, those outputs for g of x, that make f of x true. So I have to take a look at what that composition is first to decide what the domain is going to be for this new function that I've created. So remember what f composed with g means. It means f of g of x. So that means I'm going to take the rule for g of x, and I'm going to substitute that in place of the x in the function f. So I'm going to be doing f of x minus 5. Now in this case, that's pretty easy to do. F composed with g just means it's going to be the square root then of x minus 5, which is great. I made a new square root function. I have a new value. But notice what the domain would have to be for this function. This expression has to be positive. And remember, that means we have to think of it greater than or equal to 0. In this case, it definitely could be equal to 0. It's not in the denominator of a function or of a fraction. So anything that was going to make this positive or 0 is going to be okay. So you can guess and check some numbers. 6 would work. It would be 6 minus 5 would be 1. 7 would work. 8 would work. How about 5? 5 minus 5? 0, square root of 0 is 0. All those work. In other words, just solve this inequality. All the x's that are greater than or equal to 5 are going to be okay. So the domain of this new composed function is all the numbers starting at 5 and to infinity, or if you want to say x is greater than or equal to 5. Not the same as just what the domains were of the two things separately. So remember, when we look at composition, it has to be the things that are in the output of g of x. So g of x, remember, had all real numbers. I couldn't use all real numbers, so I could only use the ones that worked in this domain, which actually wasn't 0 to infinity. I couldn't use, think about that, you couldn't use 4, could you? Or 3 or 2, you get negative values. So not this entire domain of f actually works. It's only the ones that are 5 or greater. So remember, when you create a new function, you have to look at that function to decide what your domain is actually going to be. It's going to be some part of maybe what you started with. All right, let's talk about how functions are made then. I think now you're going to have a little bit different perspective when you think about these more complicated functions. They're actually compositions of a whole bunch of other functions put together. In this case, we're looking at composing 2. So we're taking 2 functions to create or make a new one. So shouldn't we be able to go the other direction? If you see something that's already put together, what pieces or parts do they compose to make that happen? So we're going to do something called decompose. Meaning like the opposite of composition, D, meaning opposite. So it sounds terrible. It sounds like, rotting fruit or something in your garbage, but decompose a function means you are looking for the 2 functions that have been put together to create this new thing, and you're trying to pull it back apart. So oftentimes what they're going to use in the textbook is they're going to call this function an h of x as a composition of f composed with g. They're just going to pick those same letters all the time. So they're going to use this new function. This function that's already been made is called this h of x. And they're trying to ask you, hey, what 2 functions could you compose to make that? So working backwards to tell what they use. So trying to figure out the f of g of x to be able to tell how did they make that function? Where did it come from? So a lot of times what that means is looking for an inner function and an outer function. So what do I mean by that? Well, if you look at it in this last way to write it, f of g of x, the way that we always do composition, the inner function is that g of x. So when I say inner, the symbolism that we'll probably use for that is g of x. The outer function then would be the f of x. So you're trying to figure out, hey, what's the function that I need to put in, and what function am I putting it into? So we're trying to break this more complicated thing down into its parts of composition. So let's just give one a try here. And there's, by the way, lots of different ways to do this. So h of x is this absolute value equation. So absolute value of 2x minus 5 plus 1. So the h of x is kind of like the final answer. So it's almost like kind of like Jeopardy. You have to figure out what the question is. So we're going to try to do this as a composition of two functions. So f composed with g of x, which means it's f of g of x. So we need this inner function, the g of x, and we need an outer function, f of x. So let's talk about it both ways. So I'm going to say g of x equals, and I'm going to call that inner just so we can keep that kind of going here. And then outer function is going to be our f of x. So what rule would that have to be? Okay, so sometimes we look for natural breaks in things. So I'm going to give you an idea of maybe something that could work. If you have something like a function like absolute value or squaring or square root or cubic, take a look at what's on the inside. So notice what's on the inside of it, 2x minus 5. That sort of naturally just being on the inside of an operation symbol is a really great idea for an inner function. So what if 2x minus 5 was my inside? So because it's already inside the absolute value. That means I'd be doing f of 2x minus 5. Now, what would I have to put that 2x minus 5 into then to get this entire thing for my answer? Well, the 2x minus 5 sure looks like it went into absolute value bars, and then you have to have an add 1 on the outside. So what if f of x was absolute value of x then? Remember, because you're replacing this whole 2x minus 5 in for x, and then we need a plus 1 on the outside. Let's see if that works. So if I did f of 2x minus 5, that would mean plug in 2x minus 5 into the absolute value, and then add 1. And sure enough, there's your h of x. So if my inner function, g of x, is the linear part, the 2x minus 5, and the outer function is x, absolute value of x plus 1, it actually makes this function h. Now, the cool thing about this is once you guess what your two functions are, just try f composed with g and see if it works. Like, do what we just did. So plug in the 2x minus 5 and see if that makes sense. And you're like, oh, yep, okay, that looks like it's working. You can check your answer. Now, is that the only way to do this? Well, no, absolutely not. There's other ways to make an inner and an outer function. So we can take a look and see if we have another option that could work. So let's try it a different way. See if you can pause the video even and come up with a different inner and outer function that would also make this true. All right, so let's talk about another option. See if anybody came up with this one. What if this entire thing was your inner function? So what if g of x was the whole deal, absolute value of 5x minus 1? Well, then what would you have to put that into? So let's think about it this way. Remember, it's f of g of x, so it'd be f of that whole thing, 2x minus 5. What would you have to put that into? Well, it looks like the only thing you have left would be just adding 1. So outer function then would just be a linear equation, x plus 1. So let's give that a try and see if that actually works. So you'd be taking this whole thing and plugging it in for x, so absolute value of 2x minus 5, and then plus 1. Yep, sure enough, that works great too. So my inner function could be that whole thing. Now, what I don't want you ever to do is just have one of your functions just be x, the identity function. That's kind of not what we're really looking for, right? We want to try to find two different rules that create or make this new one. So I'm going to have you try another one. And once you do a few of these, you do get better at it. It's almost like thinking about a puzzle and what pieces would have to come together to make this happen. So we're going to try another one. So here's your h of x. It's a cube root divided by a constant 5. And so what we're going to try to do again is we're going to try to write this as a composition of two functions. So I'm just going to use f and g again, which remember means f of g of x. So we're trying to figure out a g of x, which is this inner function. And we're trying to figure out the outer function, this f of x, that we're going to put it into. So I challenge you to think about really when you look at that whole thing together, what looks naturally kind of on the inside and what could be on the outside and how that might work. So go ahead and pause the video and see if you can come up with something. What a lot of people look at this one as inside is this 8 minus x. That sort of naturally looks like something that's on the inside of an operator. So what if g of x was just this 8 minus x? What would you be putting it into? Well, you'd have to be putting it underneath a cube root. Now notice here though, we'd just say x because we'd be putting in 8 minus x in place of the x and then over 5. So let's see if that works. Let's give it a try. We'll just practice it from the beginning. So if we wanted to do f of g of, oops, not f of f. You can do that, by the way. You can compose a function with itself. You just put the rule into itself. But we want to do f of g of x, which means we're going to do f of g of x. And our inner that we're thinking here is going to be 8 minus x. So let's just try this kind of from the beginning. In the rule, if this is our rule for f, we'd be taking the cube root then of 8 minus x. I'd be plugging it in and then over 5. Yep, works great. So inner and outer, that's a real natural way to do it. You might have a different idea though, so I challenge you to find a different way. What could be a different inner and outer function? So let's do a big OR here. What else could g of x and f of x be? Well, what if the whole numerator, this entire thing, was your inner function? So cube root of 8 minus x. What would you be putting it into? Well, the only other thing is divide by 5. So what if f of x was x over 5? Because remember that x is going to be what you're replacing your g of x for. So you need that x in that second function. But wouldn't that just give you the same exact thing if you do f of g of x? So f of the cube root of 8 minus x would be the cube root of 8 minus x, replacing for the x, over 5. So lots of different ways to do this. But again, you can't just have an x. We're looking for ways that you can take a function that's been put together and decompose it, or write it as a composition of two functions. Because in real life situations, that's often what we have, which is what we want to finish up with today. So let's talk about an application. I mentioned this at the beginning of the video. What if you're trying to calculate tax or sale price or anything like that? There's often multiple steps you have to do. If something's on sale, for example, you have to figure out what the sale price is first, and then you can calculate the tax. There's all sorts of different ways to think about these things. So you're, in other words, using more than one function. All right, so let's take a look and see what they're giving us here. So I'm going to set you up with what the scenario is. Say there's 6% sales tax. So we've got 6% sales tax on an item. So I'm going to give you some info about it. And you're going to have a 25% off sale. 25% off is the sale. So let's think about how would you calculate. We're just going to do this numerically, and then we'll get into the actual functions because it seems a lot more complicated. Which one of those things would you have to calculate first if you're going to calculate the price that you actually pay at the register? Well, you want to calculate what your sale price is. You need to know tax on how much of an item. So you'd have to figure out how to calculate the sale price. So let's see if we can figure out what that would look like. How would you calculate the sale price if it's 25% off? Well, I think a lot of people would figure out the 0.25 times the value, and then they'd subtract it off. Well, it's a little bit easier to figure out the sale price just to directly figure out how much is it going to cost you. So if it's 25% off, what percent do you pay? So what percent would you actually pay as your sale price? Well, if they're taking 25% off from the 100% of the original price, you'd be paying 75%. So to calculate the sale price, we would be doing 0.75, remember percent as a decimal, times the cost of the item. So just for argument's sake, let's say we're going to buy something that costs $100, just so we can kind of figure this out ahead. So we're going to try to figure out the answer to this question here. If I want to do a 25% off sale on a $100 item, I do 0.75 times $100, and I'd be paying on my sale price $75. Seems reasonable. Okay, so then how do I figure out, and I'm going to ultimately go down here, we're going to write a function for the sales tax owed, just for the sales tax. So how would you calculate how much sales tax there would be on a $75 item? Well, it's 6% sales tax. So the sales tax owed, we would have to take 6%, so 0.06 times your $75, and we can calculate what that is. So 6% of 75, go ahead and type that in. You get a grand total of 4.5, which means in this world, $4.50 in tax. So we could actually figure it out. Notice we took the output, or the answer for 1, and we put it in as the input for that second function. So think of it kind of like that inner and outer. We had to do this operation first, and then we had to do the sales tax. So it's a composition of functions. Now let's take a look at the specific example that they're giving you. F of x is the 0.06 times x, represents the sales tax. Well, yeah, 6% of whatever x is, which is the purchase price, the price tag. G of x is this one, represents the sale price of an item. Okay, well, of course, because if you're taking 25% off, you're paying 75%. So that's the fastest way to get to the sale price of an item. Using one of the combinations of functions that we talked about. So add, subtract, multiply, divide, composition. Write the function that represents the sales tax owed on an item of that price with a 25% off sale. So sales tax owed. All right, well, let's see if we can figure out which operation. So it looks like we did sales price first, the sale price. We calculated that and we took that answer and put it in to the tax. So we were taking the sale price first and then the tax. Okay, so which of those functions, F or G, represents finding the sale price? Well, that's the G function. So I needed to do the function G, and then I put that in for X. So if I put G in for F, how could I write that function? Well, it looks like it would have to be second gets substituted, F compose with G of X. Because I would be taking F of G of X, so I would calculate my price first, right? So I'd be getting my sales price first, and then taking that answer and calculating the tax owed. So F composed with G would be a way to be able to calculate what that value is. And let's just see when we do that function with these, if that actually checks out. So we'd be doing F of 0.75 times X. So I'm going to replace in the function F, I'm going to replace this for the X. So I take 0.06 times 0.75 times X, which is going to give me 0.045 times X. That would be F composed with G. So I need to do the sale price first and then calculate the tax. And notice then whatever your sale price is, now I can get directly to that, whatever the price of your item is, I should say, you can get directly to what the tax would be owed. Remember our $100 example. So what if your originally priced item was $100? In other words, X equals 100. You would be doing 0.045 times 100, which is going to give you that $4.50 as your sales tax owed. So sales tax owed. Sometimes it's easier to think of it with a numerical example like that to be able to do that, but that's really all composition is, right? We're doing one operation and then another. So in this case, we have to calculate the sale price first, and then we substitute that in. All right, so let's go back to our essential questions for today. We figured out how to deal with composition, that substitution, so composing one function into the other, and then how to model and use that in a real life question. Many situations are more than one function put together in real life situations. So we just need to be able to navigate that.